Hello, my name is Alex Fonseca, and today I am going to be presenting my team's project on providing access to clean water in dry, war-torn areas. So my team is a group of five. We include Jaden Jordan Caldero, who did the formatting on the poster, Alan Beachman, who did the 3D design for our core graphic, Jonathan McBride, who made the charts you'll see on the poster, Jeffrey Lowe, who made the poster itself, and me, Alex Fonseca, who was responsible for the presentation as well as some of the final research. The challenge we are addressing with our project is providing access to clean water to those in dry, war-torn, and impoverished areas. The target audience for our proposed solution includes impoverished people in nations such as Yemen, Gaza, and Somalia. These regions are all close to the ocean, yet lack widespread utilities due to ongoing conflicts. In Yemen, for example, nearly half of the population lacks access to clean and drinkable water. Our proposal primarily addresses the grand challenge of providing access to clean water, as that is our focus, though it does tie into improving urban infrastructure as well as making solar energy more economical. Our solution relies on three main components: modularization, indirect and direct solar power, and a cost offset in the form of saltwater evaporation. The core process we plan to use in order to provide clean water is multi-effect distillation absorption desalinization, also known as MEDAD. In our site mock-up, you'll notice the process starts as water is pumped into the heating tank where a solar lens is used to heat up 20,000 liters of water to 158 degrees Fahrenheit. The water is then pumped into the desalinization module where the MEDAD process occurs, which makes use of pressure gradients to distill the water energy efficiently. The absorption process at the end utilizes a silica gel to hold the fresh water and increases the operating temperature range and freshwater output. 70% of the input freshwater will be recovered as freshwater, as the input seawater will be recovered as freshwater, which equates to enough for roughly 3,800 adults per day. The remaining 30% of input is concentrated into an extremely salt-rich brine that is then passed into the salt evaporation field. We estimate that this brine can be evaporated to produce a massive $40,000 worth of salt annually. It is important to note that all of the electrified parts of the system are powered by the pictured solar panels, which is essential due to the lack of utility infrastructure in our target region. Low-cost materials are used to reduce cost and risk of theft, while modularization is used to further limit upkeep and manufacturing cost. Turning your attention to our cost graph, you'll see that this process compares favorably to other types of desalinization processes currently on the market. Please note that our projection assumes our theoretical calculated efficiencies while also factoring in the cost offsets. Looking at our technology comparison, you'll see that this type of desalinization provides some of the safest drinkable water process when compared to other established water purification methods. In our feasibility study and design shortcomings, we've listed out some of the factors that affect design feasibility or drawback to the overall project. Most important to note is that all of the technologies we've used are independently proven, but the novelty in our proposal is the combination of these technologies. Therefore, a lot of our numbers are highly theoretical and would need to be proven. We estimate that the unit as a whole would cost about $300,000 with a cost reclamation for local communities and the prospective help of NGOs. It could be possible to push this number lower. If we had more time and funding, we would first focus on building a mock-up of the design to prove the overall concept, and in the future, we'd try to find additional valuable material we can extract from seawater and find even more energy efficient ways to heat up the input water. Long term, we'd also like to address the distribution of processed water and ensuring the security of our plant, as our target locations lack widespread utility infrastructure and are prone to violence, which may put the plant at risk. This solution provides a well thought out and cost effective way to provide clean water to people in war torn areas